In this video, we're going to look at arc length and curvature. We've done arc length a couple times in calculus already, and the arc length is given to be the integral from a to b, the square root of f prime of t squared plus g prime of t squared with respect to t in our beautiful parametrics. Or we could say the integral from a to b. And we often use this notation, the derivative. They both say the derivative of x with respect to t squared plus the derivative of y with respect to t squared. So you can see where we're going here. When we put this in 3 space, we're going to add, when we put this into a vector, into R3, we're going to add the third component in. So we're going to say the integral from a to b, and using the top, I'm going to use parentheses. We're going to use f prime of t quantity squared plus g prime of t quantity squared plus h prime of t quantity squared with respect to t. Or we can call it the integral from a to b, and we have the square root of dx over dt quantity squared plus dy over dt quantity squared plus dz over dt quantity squared. I think these are easier than some, with respect to t, I think these are easier than some of the arc length formulas we have, because you don't have to determine which of the DS's to use. If that makes sense, great, and if not, let it go. Notice that we could also say that L equals the integral from a to b, the length of r prime of t with respect to t. So that's a nice, easy formula to use, because remember that when you look at r prime of t, let's make a note real quick here, that the length of r prime of t is equal to the length of f prime of t I plus g prime of t j plus h prime of t k. And if we're working in 2 space, it's the same thing, but this gives us the square root of f prime of t quantity squared plus g prime of t quantity squared plus h prime of t quantity squared. So you can see how that this length of the vector of r prime of t equals that value. So these 3 notations, these 3 formulas are equivalent. You can use whichever one you prefer. I like the middle one. It's the one that I tend to use. So that's where we're headed with this video. All right, this example says find the length of the arc of the circular helix with vector equation r of t equal to cosine ti plus sine tj plus tk from the point 1, 0, 0 to the point 1, 0, 2 pi. So we're going to say that in order to find arc length, I'm going to have to find the derivative of the components. So I'm going to start with r prime of t equals. I'm going to take the derivative. I left me a little space in there on purpose. R prime of t, the derivative of cosine of t, I, is negative sine of t, I, plus the derivative of sine of t, j, is cosine of t, j, plus the derivative of tk is 1k. So that's nice and easy. So we're going to integrate this. Now, remember that your arc length is equal to the integral from a to b of the square root of f prime of t squared plus g prime of t squared plus h prime of t squared with respect to t. Or you can call it the integral from a to b, the length of the derivative of r of t with respect to t. So you can go either way on that. Both of them are going to give us the same thing, but we need that a to b. So let's go back up here and notice that, let me switch colors. So if we go back up here, notice that t is actually k, and we're integrating with respect to t, so our bounds need to be in terms of t. So that means right here, this tells me that t equals 0, and right here, t equals 2 pi. Now you can verify that, because if you plug 0 into r of t for the first one, you get the first point 1, 0, 0. If you plug 2 pi into r of t, you get the 0.102 pi. So you can pause and check those. I would, so that you can be sure you understand. But you got to figure out what t is. So let's integrate from t equals 0 to 2 pi. And we have the square root of f prime of t is negative sine of t, quantity squared, plus g prime of t is cosine of t, quantity squared, plus, and then we have 1 squared with respect to t. This one's nice and pretty, 0 to 2 pi. So we have the square root of, we have, I'm going to write it out. We have sine squared of t plus cosine squared of t plus 1 with respect to t. So sine squared plus cosine squared is 1. I'm not going to write this out. So 1 plus 1 is 2. So we have the square root of 2 with respect to t. Now this gives us t times the square root of 2 from 0 to 2 pi. People get lost there. So remember, if you integrate 5, you get 5t. If you integrate 8, you get 8t. So if you integrate the square root of 2, you get the square root of 2t. But I'm going to put the t in front of the square root of 2. So this means we have 2 pi minus 0, which is 2 pi times the square root of 2. So this is the arc length of that circular helix with the vector equation given. Now they gave us a picture of the arc length, and so we know that the length of this arc from 1, 0, 0 to 1, 0, 2 pi is 2 pi square root of 2. We know they tend to make the exercises more complicated than the examples. So this is an example of one in the exercises. And they use the IJK notation, but I'm going to switch it and call it 1 t squared t to the third. And they define t to be between 0 and 1. So it's nice that they give you the bounds like that. Life works out good. I think they do in all of the exercises. So let's start with the fact that we have the bounds for t. So let's go ahead and find the derivative of the vector r. So the derivative of 1 is 0. The derivative of t squared is 2t, and the derivative of t to the third is 3t squared. So now we can talk about the arc length. From 0 to 1, the square root of the square root of the components here. So we're going to have 0 squared, which was a waste of our time, I know, but 2t squared plus 3t squared with respect to t. Now this is interesting because we have the integral from 0 to 1, and we have the square root of 4t squared plus 9t to the fourth dt. U sub is not going to work, but we can factor a t squared out. So let's do that. We have the integral from 0 to 1. We have the square root of t squared times the square root of 4 plus 9t squared with respect to t. So this means we have the integral from 0 to 1 t times the square root of 4 plus 9t squared with respect to t. Well, that one's nice and pretty. So now we can use u sub. I'm going to push this here, and we're going to let u equal 4 plus 9t squared. And if that's the case, then du equals, the derivative of 4 is 0, and here we get 18t dt. So dt equals 1 over 18t du. If you haven't seen u sub worked out this way, I think it's easiest for everyone, so I'm going to do it that way. But I'm going to change my bounds. Let's start with when t equals 1, we're going to plug it in and find out that u equals 9 plus 4 is 13. And when t equals 0, 4 plus 0 is 4. So our u bounds will be 4 to 13, so that means we don't need to go back to our bounds. So now I'm going to switch to u sub. So I'm going to say the integral from 4 to 13 are new u values. And we have t times the square root of u times 1 over 18t du. So the t's cancel out here. Let me do that in a different color. The t's are going to cancel. So I'm going to bring my 1 over 18 out front. We have the integral from 4 to 13 of u to the 1/2 du. That's not a bad problem. When we integrate u to the 1/2, we're going to bring down the 1 over 18. So we end up with u to the 3/2. So 2/3 is the coefficient from 4 to 13. I'm going to reduce this fraction. So I have 1 over 27 u to the 3/2. Now, we're going from 4 to 13. So 1 over 27, we have 13 to the 3 halves minus 4 to the 3 halves. Remember, 3 halves means the square root and then you cube it. So 13 to the 3 halves can't be simplified, but the square root of 4 is 2 to the third power is 8. So this is your answer right here. This is the arc length of that figure of the given vector at the top. All right. This is an interesting one that I don't want you to miss. Number 11. It says find the length of the curve correct to 4 decimal places. Use a calculator or a computer. So that means you don't need to actually integrate by hand. So let's talk about what that's going to look like on your paper for me. On a quiz or a test, it would say set up but do not integrate. So r of t equals cosine of pi t, 2t, sine of 2 pi t. And then it says from 100 to 140. So you're finding the arc length correct to 4 decimal places. So we're going to start the way we did. Let's start off with t. In the fact here that we have 2t, let's make it a little bolder here. The fact that we have 2t, this means that t equals 0, and on this one t equals 2. So I really like the problems where you have to think about t a little bit, but I don't think they make you do that enough. It's okay. So now I'm going to do r prime of t, which equals the derivative of cosine of pi t. The derivative of cosine is negative sine of pi t. And then the derivative of pi t is pi, using our chain rule. The derivative of 2t is just 2. The derivative of sine of 2 pi t is cosine of 2 pi t. And the derivative of the 2 pi t is 2 pi. So this is our really pretty derivative integral, our derivative vector. So now we're going to find the arc length, which is the integral from 0 to 2. And we have the square root of, I'm going to go ahead and square it and say pi squared sine of pi t quantity squared plus 2 squared is 4 plus, when I square this, I get 2 times 2 is 4 pi squared parentheses cosine of 2 pi t squared. Now you need to be sure that you have all of that in parentheses, and this is with respect to t. So on a TI-84, if you hit math and then you hit F integrate, you can use your calculator to find the integral, and that's what you're supposed to do here. Arc length often isn't done by hand because the stuff that's involved. So if you hit math and then just go straight to F integral, it should give you how to do that. If you need further help on that, let me know. Here you can see my graphing calculator, and I have it on my phone. You can't use your phone during the test, but there is an app for that. So in the top one, in the top line, I used parametrics. So when I hit the variable function, I automatically popped up with the t. And you could use it in x in terms. I'm not sure if you know how to use your calculator. But our arc length then to the nearest 4 decimal places, it said, would be 10.3311. Arc length is often something that's only pretty in a math book, so lots of times it's used on a calculator. The last one wasn't bad, so there will be times where I ask you to work it out, and there will be problems that say set up and then use your calculator to solve. So I'm looking for the work to get to this point, then you can plug it in your calculator to come up with the answer. And you can see that I'm using the TI-84 as most of you have. Okay, look at this picture here. So what we have is we have vector r of t in our normal definition, f of ti plus g of tj plus h of tk, where t is between a and b. And then note that r prime of t is continuous and c is transversed once as t increases from a to b. So then we're going to, what we have is we have this figure happening up here. So then we could define its arc length in terms of a variable s, and that's going to come in a minute. So just trust me. We're going to say s of t. This is our new arc length. It doesn't change anything. It's going to get us to where we're going. We're talking about the arc length function, and we're going to we're going to parametrize the curve with respect to arc length, just so you know where we're headed. But the arc length function S, let's call it arc length function S, in terms of t equals the integral from a to t. Notice that what we're talking about is we're talking about a piece of the curve. We're talking about stopping right here. As I do it in blue, so let's try it again. We're talking about the piece of the curve right from here to here. So this is our arc length function where we're stopping somewhere along the interval. So this arc length is the length of r prime of u. We're going to have to use a different variable, not t, because we're integrating from a to t. So this is the integral from a to t of the square root of dx over du, quantity squared, plus dy over du, quantity squared, plus dz over du, quantity squared with respect to u. So this means, notice that we're using u as our variable. I forgot the other half of the arc length. We're using u as our variable as we integrate. So this is the length of the variable between r of a and r of t. That's why our bounds are from a to t. So this arc length function is going to be important, and it's going to be used to help us parameterize a curve with respect to arc length. That's important here. Parameterize a curve with respect to arc length. So what we're going to do is we're going to take this piece of the curve that we have up here in our S of t, the small part of the curve, and we're going to put it back into parametric equations so we can put it back into vector r. So the steps here are we're going to use the arc length function to find our arc length in terms of t. Use the arc length function to find arc length in terms of t. You may need to pause to write, and that's okay. Secondly, we're going to solve for t as a function of s. So we're going to find, hint, we're going to find t of s. And then thirdly, we're going to substitute t. Substitute for t. So it becomes r of t of s. So that's how we're going to parameterize a curve with respect to arc length. So let's look at one of those. Sadly, they're boring and use the same example again and again. So here's an example where it asks us to reparameterize the helix r of t equals cosine of ti plus sine tj plus tk with respect to the arc length measured from 1, 0, 0 in the direction of increasing t. So we know that in order to do arc length, the first thing we're going to need to know what t is here, and t is 0, as we talked about before. And we also need to find r prime of t to find the arc length. So as we did before, r prime of t equals the vector. The derivative of cosine of t is negative sine of t. The derivative of sine of t is cosine of t, and the derivative of t is 1. In order to reparameterize the helix, the first thing we need to find next is s of t. Remember that s of t is the integral of the arc length from a to t in terms of u. So I'm going to use this notation because it's faster to write. But the thing to notice here is our variable is going to be in terms of u. So we're going to say s of t equals the integral from a, that's our beginning t value, which we know from way up here to be t equals 0. So from 0 to t, and I'm going to do the square root of negative sine of u squared is sine squared of u, plus cosine squared of u, plus 1 squared is 1, and with respect to u. So then we have s of t equals the integral from 0 to t. Now sine squared plus cosine squared is 1, plus 1 is 2 du. So this gives us u times the square root of 2 from 0 to t, which is t minus 0 times the square root of 2. So that tells us right down here, we can say that s of t equals t times the square root of 2. That's the first step in our reparametrization. The next step is, well, remember the first thing was to find the integral, and then we need to solve for t in terms of s. So I'm going to rewrite this here to say s equals t square root of 2. So we know that t equals s over the square root of 2. So that's the second step, is to write t in terms of s. And then our last step is for the reparametrization, is to use our original r. Let me bring it back onto the screen because I think it might be gone. So we're going to go back to our original r, and it's going to be in terms of the arc length that we're looking at. So instead of r of t, it's going to be r of t of s. So then we can use this to say, let's not go there. Let's go over here. We're going to say r of t of s equals cosine of, instead of t, we're going to use t equals s over 2. So we have cosine of s over the square root of 2i plus sine of the square root of s over the square root of 2j plus, instead of t, we have s over the square root of 2k. So this is the reparametrization of the helix into the direction of the increasing t. So it's not too bad. It's not too bad. You need to pay attention to this formula. And so you're going to solve for t in terms of s and then put it into your original vector. And notice that that gives you your parametric equations in terms of the arc length. So we would say x equals cosine of s over the square root of 2, y is equal to sine of s over the square root of 2, and z is equal to just s over the square root of 2. So it's not a bad process. It's actually very interesting. So let's look at another problem. Going back to arc length real quick. So this problem says, let C be the curve of intersection of the parabolic cylinder x squared equals 2y and the surface 3z equals xy. Find the exact length of C from the origin, 0, 0, 0. And I know that you know that, but if we write it in, then I'm less likely to forget about it, to the point 4, 8, 32 over 3. Now, the parabolic cylinder tells me that we are in a vector space. We're in 3 space. So we're going to take this, and let's start off with this x squared equals 2y. So this is going to work better if we put it into 3 space and use parametric equations. And that's the key that you have to get here, that it doesn't tell you that, you just kind of have to figure it out. So we're looking at the curve, and we're going to think about all these things. Now, when this happens, you can say x squared equals 2y, or you can say y equals 1/2 x squared. But in either case, the z is 0. So keep that in mind, z is 0 in this case. Now, I'm going to let x equal t. Now, when I do, then I can say that y equals 1/2 t squared. So you can see our nice parametric equation here. Now, c also lies on the surface of 3z equals xy. Since we have 3z equals xy, we know, let's change this to our parametric equation as well. But you can't just define the variables now. We're going to use the ones we used above so it carries some continuity. So we're going to say 3z equals x, which is t, times y, which is 1/2 t squared. So this means that 3z equals 1/2 t to the third. My z's and my t's are starting to look alike. Be careful about that. Now let's solve it for z. So z equals 1/3 times 1/2 is 1/6 t to the third. Now that we have our z in terms of a parametric equation, we know that here we have parametric equation for x, one for y, and one for z as well. So we can go ahead and say our vector equation for this is t, 1/2 t squared, and 1/6 t to the third. So we have our beautiful our beautiful vector equation. And we are given these 2 points, the origin. Now at the origin, we can look at the x value because that's t. So that means we're going to say that we start at t equals 0 and we finish at t equal 4. And if you plug it into each of those values, you'll see that it's true. Now let's go back to the problem. And the problem says, find the exact length of the curve. So we're looking for arc length. I'm moving this up so we have room to look at it. We know that we need the derivative in order to find the arc length, so let's do that. The derivative of t is 1. The derivative of 1/2 t squared would be 2 times 1/2 is 1 t. And the derivative of 1/6 t to the third is 3/6, which is 1/2 t squared. So now we have our derivative. Now we can find our arc length, the integral from 0 to 4, and we're going to do the square root of 1 squared is 1, plus t squared is t squared, plus 1/2 t squared is 1/4 t to the fourth with respect to t. Now it says an exact length, so that means you can't use a decimal, you can't use your calculator, but this factors pretty. It factors into 1 plus 1/2 t squared times 1 plus 1/2 t squared, back to t. Now I know I didn't have to write it twice, I could have written it once with the squared, but some of you will see it better this way. Then the squared and the square root cancel, so we have the integral from 0 to 4, 1 plus 1/2 t squared with respect to t. Now that's not a bad integration, so when we integrate it, we get t plus 1/2 times 1/3 is 1/6 t to the third from 0 to 4. So this means we have 4 plus 4 to the third is 64/6, which reduces to 32/3, minus zeros. So 4 plus 32/3 equals 12 plus 32 is 44/3. So that is the exact arc length of the curve of the intersection of the parabola and the parabolic cylinder and the surface. Before we move to the next topic, you have a problem that looks like this. It says find, correct to 4 decimal places, the length of the curve of the intersection of the cylinder and the plane. So you have to note that this first equation that you're given, the cylinder here, this is elliptical. So when you do this, you have to set your parameters. So the way this works is x squared and y squared always make sine and cosine. So when you see this, we're going to let x equal cosine of t, and y equals the square root of 4, which is 2 sine of t. And it has to do with the fact that if you solved it to be x squared, divide everything by 4, so you go to x squared plus y squared over 4 equals 1. That's where this comes into play. So to find the intersection of that with the other one, we're going to say x, we're going to use this equation, and we're going to say z equals negative x minus y minus 2 or plus 2. So z equals, the x is cosine, so we have negative cosine of t, minus y is 2 sine of t, plus 2. So our vector for the intersection of the two curves, the first component is cosine of t, that's our x, because we have our parametric equations here, like we did in the last one. So y is 2 sine of t, and z is negative cosine of t minus 2 sine of t plus 2. So then you're asked to find the arc length, and I think that you can do that. I just wanted to help you get the setup of this because it's a little interesting. So then you'll find your derivative of the vector r, and you'll find arc length from there. The next part here looks at curvature, and the parameterization r of t is called smooth on an interval I if r prime is continuous and if r prime of t does not equal 0 on the interval. So we define smooth in algebra with it has no breaks and no sharp turns. But here a curve is called smooth if it has no sharp corner or cusp. So when the tangent vector turns, it does so continuously. You can see all these tangent vectors happening here. Now, if t is a smooth curve defined by the vector r, remember that our unit tangent vector, so our unit tangent vector is equal to r prime of t over the length of r prime of t. And the unit tangent vector indicates the direction of the curve. From the figure here, you can see that as the unit tangent vector changes direction, it does so very slowly when c is kind of close to straight, but it changes direction more quickly when c bends or twists more sharply. So the curvature of the curve at a given point measures how quickly the curve changes direction at a point. So the curvature is how quickly the curve changes direction at a point. How quickly the curve changes direction at a point. So we can say that we can also define curvature to be the magnitude of the rate of change of the unit tangent vector with respect to the arc length. So arc length is used so that we don't have to deal with the parametrization. It doesn't matter what's happening there. Because the unit tangent vector has a constant length, only the changes in direction contribute to the rate of change of t. So we have a definition of curvature. I'm going to leave this here. And let's say the curvature, this is the definition that we're going to use. The curvature uses the Greek letter kappa. So instead of writing the formula for you, I brought in the Greek letter kappa. Now I didn't do arc length in terms of ds, so let's look at a more practical formula. So this formula is our formula for curvature, and it's our Greek letter kappa, and it's the derivative of the length of the unit tangent vector over the derivative of the length of r of t. So that's the formula we're going to use to find curvature. And remember that we talked about curvature, and it's the measure of how quickly the curve changes direction at that point. So we can say it's the magnitude of the rate of change of the unit tangent vector with respect to arc length. But I really like to think of it as how quickly the curve changes direction at a point. So you're often asked to find curvature. This formula here is nice and succinct, but it's not as easy to apply as the next one. So before we look at one of these problems, I'm going to give you the next formula for curvature. This is the formula for curvature that you want to write down because this is the easier one to use. I'm going to show you why as we work through an example and explain to you why why you want to use this one and not the other one. So it says the curvature of the vector function is given by kappa of t equals r prime of t cross product with r prime of t and the length of that over the length of r prime of t to the third power. So this one is easier to use. It's more applicable. We won't use the above one. I'm going to show you why as we do a problem. So let's look at a curvature problem. So we're supposed to find the curvature of the vector r of t, which equals 2t squared ln of t, t ln of t at the point 2, 0, 0. So if you look at this definition, we need to find r prime of t, r double prime of t, the first derivative and the second derivative of the vectors. So let's talk about the first derivative of this vector. The first derivative of this vector is the derivative of 2t squared is 4t, and the derivative of natural log of t is 1 over t. And then I'm going to work this out over here. We're going to let z equal t ln of t. So the derivative is, we take the derivative of t to be 1 ln of t, plus we take the derivative, we keep the t, and the derivative of ln of t is 1 over t. So the derivative is natural log of t plus 1. No parentheses there. Natural log of t plus 1. So this is our first derivative. Now let's go ahead and find our second derivative, which is the derivative of 4t is 4. The derivative of 1 over t is negative 1 over t squared. So using that similar mode, let's say that we have t to the minus 1, and when we take the derivative of that, we get negative t to the minus 2. So that's where that comes from. The derivative of natural log of t is 1 over t, and the derivative of 1 is 0. So that's our second derivative. Now, if we were using the curvature definition up above, we would need the unit tangent vector, which the unit tangent vector says the derivative of r over the length of the derivative of r of t. So then you're going to find the derivative of that. In order to do that, there's a whole lot happening in the derivative of that unit tangent vector for this part. That's why the other one is easier to use. So you can kind of see if it's a mess. I was going to show you both of them, but I decided you didn't want to do that at all. So you can work it out on your own if your heart so desires. We have to find the cross product, and we're supposed to find it at the point 200. So think about this. If I let this happen, since the first component is 2t squared, then t probably is 1. So if I plug it into each of the components, it makes it true. Therefore, t is going to be 1. So let's find r prime of 1 to be 4, 1. Natural log of 1 is 0 plus 1 is 1. And the second derivative at 1 to be 4, negative 1, 1. Hopefully that makes sense to you. Now we can find kappa of t, which is the curvature. My kappa doesn't look very Greekish, so I apologize for that. So kappa of t is the length of r of t cross r double prime of t over the length of r of t to the third. Well, we got that one. So now we just need to do the cross product. So remember the cross product, which is good because it's good to remind you, r of t cross r double prime of t equals, let's set up our matrix ijk, and the first row is 4, 1, 1, and the second row is 4, negative 1, 1. I don't know if you remember, but 4, 1, 1 used to be information, so that's kind of interesting there. So we're going to do I times the cofactors of 1, 1, negative 1, 1, plus j times the cofactors of 4, 1, 4, 1. That's interesting. Oh, that's a minus j. Remember that. And then we have plus k times the cofactor matrix of 4, 1, 4, negative 1. All right, I'm going to go use my pencil. If you've been watching these videos, then you know that this helps me out. It could help you out as well. It helps keep me on task to write what I'm doing. And then we can go back into these. So here I have a plus 1, and we have a minus negative 1, which is a plus 1. So we have 2i. And here we have a plus 4, and here we have a minus 4, so that makes a 0 on the j. I'm going to go ahead and write 0j, because if I write my components, it would need to have a 0. And then here we have a minus 4, and we have another minus 4, so that makes minus 8k. So I'm going to put it into my pretty vector notation that we've been using, 2, 0, negative 8. And that's the cross product here. Now, for our kappa, we need the length of the cross product over the first derivative to the third power. And remember, kappa is our curvature. That's what we're working towards. So the length of the cross products, we're going to do the square root of 4 plus 0 plus 64, which is the square root of 68. And on the bottom, I'm going to do parentheses, the length of r prime of 1. I brought that down here. So we have 4 squared is 16 plus 1 to the third power. So we have the square root of 18 to the third power. So we have the square root of 68 over 18 square root of 18. The square root of 68 simplifies to be 2 times the square root of 17. And then I have 18 times 3 times the square root of 2. So this becomes 9. So we have the square root of 17 over 27 square root of 2. Now they don't always make you rationalize it, but you got square roots happening all over the place. So this is the square root of 34 over 54. And that's the curvature of this vector. We have a special case of plane curve where y equals f of x. And you can read all of that. We let x be the parameter, so r of x equals xi plus f of xj. I said you could read it, and I'm reading it to you. The first derivative ends up being accordingly. So we're given this beautiful formula here for kappa. For me, you don't need to memorize this formula, but you will need to be able to use it. It's not a hard formula to use. I don't think I'm going to walk you through it. Notice it's the length of the second derivative of x. And then the denominator is 1 plus the first derivative squared to the 3 halves. So it looks kind of like your arc length formula from earlier in calculus. All right, I decided to do one for you. So kappa says, let's start with the second derivative. So here we have y equals x squared. So since y equals x squared, let's start with finding the derivatives. The first derivative, let's let f of x equal x squared. So the first derivative is 2x, and the second derivative then is 2. So then our kappa formula of x equals the absolute value, it has to be absolute value because you don't have a vector here, of the second derivative 2, nice, over bracket 1 plus the first derivative 2x quantity squared. So we're going to call it 4x squared to the 3 halves. Now if I needed a general formula, I would go ahead and say 2 over 1 plus 4x squared to the 3 halves. And that would be my general formula to find curvature for anything at any point. So we're asked to find it specifically. Our kappa is at 0, 0, first of all. So this is the first one. We plug in 0 and we get 2 over 1 plus 0 is 1 to the 3 halves. So the curvature here is 2. And then we can find kappa at x equal 2. So we have 2 over 1 plus, and then 2 squared is 4 times 4 is 16 to the 3 halves. So we get 2 over 17 to the 3 halves. If it wants an exact answer, it may take it that way. If not, the decimal is about 0.03. So remember, the curvature tells you how quickly it's changing direction, but it was also defined as the magnitude. So you can see why the absolute value is in that formula. And we can look at the graph of this. You can see the graph of y equals x squared and the kappa graph, which is the curvature there. At any given point on the smooth space curve r of t, you can see the curve here in blue. There are many vectors orthogonal to the unit tangent vector t of t. Here's our vector right here, our unit tangent vector t. We're going to pull out 1 because the length of this unit tangent vector is 1 by definition of a unit tangent vector. So t prime of t is orthogonal to t. Typically, t prime is not a unit vector. So t prime is not a unit vector typically, but any points where the kappa is not 0, we're going to define the unit normal vector n of t, our vector notation. So we're going to say n of t is equal to t prime of t over the length of t prime of t. Now we can think of the fact of this normal vector as indicating the direction at which the curve is turning at each point. So our normal vector is going to be perpendicular to t. Normal is another word for orthogonal or perpendicular. Now that leads us into the binormal vector. The binormal vector, so we're going to say b of t equals the cross product of t and n. An interesting note to make is it's perpendicular to t and n, and it's also a unit vector. So it's a binormal vector. It's b of t is perpendicular to both t and n, and it's a unit vector. So we're supposed to find the unit normal and the binormal vectors for the circular helix that we've looked at before. So let's start off with the fact that n of t that's our normal vector, and it's perpendicular to the unit tangent vector, is the unit tangent, the prime of the unit tangent vector over the length of the prime of the unit tangent vector. We've used this before. And I'd like to make the note here that our unit tangent vector of t equals r prime of t over the length of r prime of t. All right, so let's start off with, we have r of t. Let's start off with r prime of t. I'm going to worry about I didn't make the notes for the binormal vector because I figure we won't be on the screen anymore by that time. So r prime of t, if r of t is cosine of t, then the derivative is negative sine of t. The derivative of sine is cosine of t, and the derivative of t is 1. Now we're supposed to find now we need the length of r prime of t, which equals the square root of sine squared t plus cosine squared t plus 1. I feel like we're doing the same problems over and over. So 1 plus 1 is 2, so the length of r prime of t is the square root of 2. Now let's look at t of t, the unit tangent vector. It's r prime of t over the length of r prime of t. So r prime of t is negative sine t, cosine t, 1. And the length of r prime of t is the square root of 2. So we're going to pull this out front, 1 over the square root of 2, negative sine of t, cosine of t, 1. So that's our t of t. Now let's talk about t prime of t because we need that for the derivative of the unit tangent vector. I'm going to keep the 1 over the square root of 2 out front. And then the derivative of negative sine is negative cosine of t. The derivative of cosine of t is negative sine of t. And the derivative of 1 is 0. So now our n shouldn't be too difficult to find. Our unit normal vector, n of t, equals t prime of t, which is 1 over the square root of 2, times the vector negative cosine t, negative sine t, 0. And the denominator is the length of that. So I'm going to distribute the square root of 2 and say cosine squared t over 2 plus sine squared t over 2 plus 0. So this gives us 1 over the square root of 2, and we have the vector negative cosine of t, negative sine of t, 0 over cosine squared plus sine squared is 1, so we have the square root of 1 over 2. Since these match, they cancel, so I'm going to make a note here that n of t equals negative cosine of t, the vector negative sine of t, 0. All right, so that's our unit normal vector right here. Not too bad mathematically. Now, in order to find our binormal vector, we have to take the cross product of t of t and n of t. Now, t of t is up here, and n of t is down here. So I'm going to set up my matrix for my cross product of b of b, b of t. So I'm going to start with negative 1 over 2 square root of 2 sine t, and then I have 1 over the square root of 2 cosine t, and I have 1 over the square root of 2 for the third piece. I could go back and do my ijk now. If I'd started there, I wouldn't have enough room. My matrix would be too small for all the trig. N is negative cosine of t, negative sine of t, and 0. So we've got I, and our cofactor matrix is 1 over the square root of 2 cosine of t, 1 over the square root of 2, negative sine of t, 0, minus j, negative 1 over the square root of 2 sine of t, and 1 over the square root of 2, negative cosine of t, 0, plus k, negative 1 over the square root of 2 sine of t, 1 over the square root of 2 cosine of t, negative cosine of t, negative sine of t. Now, if you've been watching the videos, you know that I like to draw my pencil lines to help me focus on my multiplication. So it's never a bad thing in my opinion. Let's go ahead and multiply. So we have I. We have 0 down here, so we have minus 1 over the square root of 2 sine of t, I. And we have a 0 down here, so we have minus, oh, that happened over here, minus, plus. So we have a plus 1 over the square root of 2 cosine of t, but it's a negative j, so we have minus 1 over the square root of 2 cosine of t j, plus, I say plus. Here we get, on this diagonal, we have a negative and a negative, which makes a positive, 1 over the square root of 2 sine squared of t. And this way we have a negative, negative, which makes a positive 1 over the square root of 2 cosine squared of t. So our k says 1 over the square root of 2 sine squared plus cosine squared. Let's just go ahead and call that 1. So we end up with 1 over the square root of 2. So we could say 1 over the square root of 2, and our vector is sine t, negative cosine t, and 1. So this is our binormal vector. Now remember, your binormal vector is perpendicular to both t and n, and it's a unit vector. So that's how you find your binormal vectors. This figure here, figure 7, illustrates the example that we just looked at by showing the vectors t, n, and b at 2 locations on the helix. So you can see them right here on the right. And in general, the vectors t, n, and b starting at various points on the curve form a set of orthogonal vectors called the t and b frame that move along the curve as t varies. This plays an important role in the branch of mathematics known as differential geometry and its applications to the motion of a spacecraft. So I thought you might find that interesting. For this example, we're supposed to find the unit tangent, the unit normal, and the binormal vectors, as well as the curvature for the following curve. So let's start with r prime of t, because in order to find the unit tangent vector, we need r prime of t. So the derivative of t is 1. The derivative of square root of 2 ln of t is square root of 2 over t. And the derivative of 1 over t is negative 1 over t squared. And notice it's the point 1, 0, 1. So we know right here that this is t is 1. So let's go ahead and make that note. At some point, we're going to need that. Now, we're supposed to find the length of r of t in order for the length of r prime of t in order to find our unit tangent vector. So this would be 1 plus 2 over t squared plus 1 over t to the 4th. Now that's interesting. So let's go ahead and find a common denominator of t to the 4th. And I need to write it out. So if you need it, it's going to help you out. This is going to be 1. We have to multiply the second one by t squared. And we need to multiply the first one by t to the 4th. So this means that we have the square root of t to the 4th plus 2t squared plus 1 over the square root of t to the 4th is t squared. Now this factors nicely into t squared plus 1 squared. And on the bottom I have a t squared. So these cancel. So we have t squared plus 1 over t squared. There are people who want to tell me those t squareds cancel. They're wrong. Don't fall into that trap. All right, so then our unit tangent vector is t of t equals r prime of t, which is 1 square root of 2 over t, negative 1 over t squared over the length of r of t, which is t squared plus 1 over t squared. So let's flip that complex fraction and say t squared over t squared plus 1. And then we have the vector 1, square root of 2 over t, and negative 1 over t squared. So if we, let's keep the denominator 1 over t squared plus 1, but let's distribute the numerator. So we have t squared, and then that 2, the square root of 2, and the t's will cancel to be t squared of 2. And then we have negative 1. T squareds cancel completely. Now we need to find the derivative of the unit tangent vector. So before we do that, let's let y equal 1 over t squared plus 1, because we need to find the derivative of that. I'm going to call it t squared plus 1 to the minus 1. You can use quotient rule, but I prefer chain rule. So then the derivative y prime of something to the minus 1 power is minus 1 times that something to the minus 2 power, and the derivative of the inside is 2t. Then we have negative 2t over t squared plus 1 quantity squared. So that's going to help us when we find our derivative of the unit tangent vector. So let's go ahead and say t prime of t equals, now we're going to have to use product rule, so we have this fraction times this vector here. So the derivative of the fraction is negative 2t over t squared plus 1 quantity squared, and we keep the vector just like it is, plus, now we're going to keep the fraction the same, and we take the derivative of the vector component-wise to be 2t square root of 2, 0. Now the good news is when we find our unit tangent vector, we don't want to find the length of that generally, so we're going to go ahead and plug in the value of 1. So we have negative 2 over 1 plus 1 is 2 squared is 4. And then we have 1 squared root of 2, and minus 1, plus 1 plus 1 is 2. And we have 2 square root of 2, 0. So let's keep going with this. So we have negative 1/2, and we're going to distribute that to be negative 1/2, negative square root of 2 over 2, and positive, I'm not going to write my positive, 1/2, plus half of 2 is 1, square root of 2 over 2, and 0. So let's go ahead and put this together. T of 1 equals negative 1/2 plus 1 is positive 1/2. Negative square root of 2 plus square root of 2 is 0. And here we have 1/2. So you can leave it like that, or you can call it 1/2, 1, 0, 1. So you could factor the 1/2 out. Either way works. And that's our derivative at 1. Now we have to find the length of the derivative at 1. Let's change colors again. So the length of the derivative at 1 means I'm going to do the square root of, I'm going to use the fractions. So I have 1/2 squared is 1/4 plus 0 plus 1/4. This gives me the square root of 2/4, which is the square root of 2 over 2. So our unit normal vector is equal to t prime of t, let's put 1 in there, t prime of 1 over the length of t prime of 1, which is 1/2 times the vector 1, 0, 1 over the square root of 2 over 2. Now, we learned in geometry these 2's cancel out nice. Trigonometry, these cancel nicely. So we end up with 1 over the square root of 2 times 1, 0, 1. And that is our normal tangent vector here. Now we're also asked to find the binormal vector. So the binormal vector is b of t equals t of t cross n of t, which equals, let's leave the 1 over the square root of 2 out front, but let's come back up here. T is actually way back up here. This one is t. This one in the green box is t. But we're going to use t of 1. We didn't actually find t of 1. So let's take a second, and when we plug in 1, we can say that t of 1 equals 1 over 1 plus 1 is 2. And we have 1 square root of 2, negative 1. So b of 1 is t of 1 cross n of 1. So remember, we just wrote down t of 1 is 1/2. I'm going to pull the 1/2 out here, the coefficient, and the coefficient of n. And then we can set up our matrix, ijk. And t of 1 is 1 square root of 2, negative 1. And n of 1 is 1, 0, 1. So we're going to have 1 over 2 square root of 2, and then we'll have everything else. And we're going to do I times the matrix, square root of 2, negative 1, 0, 1, minus j times the matrix, 1, negative 1, 1, 1, plus k times the matrix, 1 square root of 2, 1, 0. Now, I like my diagonals to be drawn, so I'm going to take a second and do that. So we have 1 over 2 square root of 2, and this would be the square root of 2 and 0. So we have the square root of 2, I, and this will be 1, and minus the negative 1 becomes plus 1, so we have minus 2j. And this is 0 and negative square root of 2, so we have minus the square root of 2k. I'm going to put it into our vector notation. So we have 1 over 2 square root of 2, and let's use this notation, negative 2, negative square root of 2. So let's distribute all of that. So I'm going to say the square root of 2's cancel here, so you get 1/2. The 2's cancel here, so you get negative 1 over the square root of 2. And the square root of 2's cancel here, so you get negative 1/2. Now, you could write this in lots of different ways. The textbook would actually factor out a 1/2, so that would be an interesting factoring, but I like this answer. So this is the vector, the binormal vector at 1. Now, the last thing we were asked to find, so this problem just keeps going, is the curvature at 1. So the curvature at 1 is equal to the length of the derivative of the unit tangent vector at 1 over the length of the derivative of r at 1. So we found the length of our unit tangent vector at 1 way back up here, right here, to be the square root of 2 over 2. And r prime, we didn't find r prime at 1. Let's do it right here. So r prime at 1, the length of that would be 1 plus 1 is 2 over 1 squared, which is 2. So we're going to fill this in to be the square root of 2 over 2 over 2. I don't know about you, but I have to think about that every time. So the phrase now is keep, change, flip. So it's the square root of 2 over 4. So that's the curvature at 1. So we have now found all the pieces, and we can continue on. The last topic here is the topic of torsion. And the torsion of a curve, I probably should have written a capital T here. The torsion of a curve that use tau is negative the derivative of b in terms of s with the dot product of the unit normal vector. Now, they use the chain rule to show all this, but the way we're going to see it is t of t is equal to negative the derivative of the binormal vector and the dot product of the normal vector, the unit normal vector, over the length of the derivative of r of t. So you don't need to memorize this formula. You need to have seen it and used it. So there is one of them in your homework. So the problem says find the torsion of the helix. Now this example says find the torsion of the helix, and it's r of t equals cosine of t sine of t t. We did this problem earlier, and we already found all of these things. So I'm going to scroll back and find that stuff. I'm going to do it that way. So we found r prime of t. Well, this we can do pretty easily anyway. The derivative of cosine is negative sine of t. The derivative of sine is cosine of t, and the derivative of t is 1. But while we did this problem, we found the length of r of t. We might as well do it again. Equals the square root of sine squared t plus cosine squared t plus 1, which is the square root of 2. So we've got that. Now we also found n of the normal unit tangent vector, the unit normal tangent vector, to be negative cosine of t, negative sine of t, 0. And we found the binormal vector to be 1 over the square root of 2 times the vector of sine of t, negative cosine of t, 1. So we have all the pieces to find the torsion. Before we keep going, the torsion at a point on a curve measures how much the curve twists. It gets into the osculating plane and whether it twists in or out of the osculating plane. But I didn't make you do the osculating plane, so if you want to go look it up, I'll let you. But it's interesting. So let's keep going. The torsion then needs b prime of t. So let's find that. So we have b prime of t is equal to 1 over the square root of 2. The derivative of sine is cosine of t. The derivative of negative cosine of t is positive sine of t. And the derivative of 1 is 0. Now we're supposed to take the dot product, the negative dot product of b prime of t and n of t, the binormal and the unit normal vectors, and then we're going to put it over the length of r prime of t, which is the square root of 2. Now the torsion is going to be tau of t, which equals negative that dot product. So we're going to do 1 over the square root of 2, and negative cosine t times cosine t is negative cosine squared t, plus negative sine t times sine t makes it a minus sine squared t, plus 0 times 0 is 0. And the denominator is the square root of 2. So this means we have negative 1 over the square root of 2, and that makes negative 1. Cosine squared plus sine squared is 1, and there's a negative in front of both, over the square root of 2. So this means that we have positive 1 over the square root of 2 divided by square root of 2, which is 1 over the square root of 2. So we get 1/2. So tau of t equals 1/2. And that is the torsion of the curve, which talks about how much a curve twists at p. So before we wrap up this lesson, these are your important formulas from this section. You have your unit tangent vector, your unit normal vector, your binormal vector, and your curvature. So make notes of these, and I hope that you understand this lesson. Let me know if you have any questions. Have a great day.